Hi everyone, I am Geeta, Assistant Professor, Department of Mathematics, SNS College of Technology.
We team from mechatronics department. I am Pradeep. Myself Sabrish.
Myself Dani. Myself Kumar Group.
Myself Karthikesh.
Myself Prince Galvin.
Myself Pranosh.
Okay. Dear all, in this session we are going to discuss about case study on Cayley-Hamilton theorem and the reduction of quadratic to canonical form in your domain, right? So, what is Cayley-Hamilton theorem? Anyone can say?
Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation.
Yes, every square matrix satisfies its own characteristic equation. What are all the uses of Cayley-Hamilton theorem?
It is used to find power and inverse of a matrix.
Good. Power and inverse of a matrix, inverse of a square matrix. Okay, right. Okay. So, for a reduction of quadratic to canonical form, first of all, we convert the quadratic form to matrix form. After that, we should find the characteristic equation and the corresponding eigenvalues and the eigenvectors. After that, we diagonalize the matrix. Okay, after diagonalization, we should convert the form into canonical. Okay, now you people search one case study on Cayley-Hamilton theorem, and you people search one case study on reduction of quadratic to canonical, right?
Today we would like to present a small case study on Cayley-Hamilton theorem. First of all, Cayley-Hamilton theorem states that in every square matrix satisfies its own characteristic equation. In simple terms, it reduced high power and matrix into much simpler usage. This becomes every useful with we deal with the dynamic systems and controls which are the backbone of our mechatronics. Let us take an example. Imagine a two-joint robotic arm used in automation. The motion of the joints can be described using matrices in a state space form. To predict how the arm will move with time, we need to calculate something called the matrix exponential. Normally, this involves heavy computation, but using Cayley-Hamilton, we can reduce the calculation and express the motion in a much simpler way. This makes the analysis faster and more practical for engineers.
Good.
In short, this theorem is not only a mathematics theory, but in mechatronics, it became a powerful tools like robotics, automation, and control system designing in a helpful for engineering smart machine.
And now we are going to discuss about reduction of quadratic to canonical form. First of all, in the field of mechatronics engineering, designing systems like robotic arms, drones, and precision machines involves analyzing complex dynamic behaviors. These systems often exhibit vibration and energy interactions across multiple axes, especially when there are joints or moving links involved. To analyze these interactions mathematically, engineers commonly use quadratic form expressions that model the energy or motion in a system. However, these forms can become complicated due to cross terms which represent coupling between variables. In such cases, the technique of reducing the quadratic from the canonical form becomes essential for simplifying analysis and improving design.
So my part is problem statement. A mechatronics engineering team was working on a 2 degree of freedom robotic arm used for assembling delicate electronics components. During testing, they observed irregular vibration at the joint, affecting the precision of the arm and end effector. The vibration behavior was modeled using a quadratic form that includes cross product terms, which show the vibrating along the x and y directions were not independent. The presence of these terms made it difficult to identify the primary discussion of vibration, analyze how energy was distributed in the system, design effective damping and control strategies.
I like to start about approaching in that there are four subheadings like modeling the system, matrix representation, finding principal direction, void and transformation. Modeling the system.
The system explores the vibration energy in the form of quadratic equation involving displacement along two directions. Matrix representation. They represent the quadratic form as a symmetric matrix, making it easier to analyze mathematically. Finding principal direction. By computing the eigenvalues and the eigenvectors of the matrix, the team discovered the principal direction of vibration. Quadratic transformation. Using the eigenvectors, the team transferred the quadratic system. This rotate alignment the new axis with the principal direction.
I think this case study highlights how reducing a quadratic form to canonical form is a powerful tool in mechatronics engineering. It transforms complex coupled systems into a simpler, decoupled forms that are easier to understand and control. In this project, the method not only simplified the vibration analysis of a robotic arm, but also directly contributed to improved performance, precise, and system reliability.
Thank you. Thank you for your good cooperation.
Thank you.
Thank you.